the fastest, the strongest, the most powerful among its peers. Meet the XY6509. Hello everyone. This video will be a review of the XY6509 step-down DC-DC converter. It's an inexpensive and compact device that can produce over 500 watts of output. If any of my viewers think I've already reviewed it, you're very much mistaken. Last time, it was the XY6509, but they only look the same at first glance. In reality, they are very different. The converter I'll be discussing today, the XY6509, has a rated output of 600 watts, but can be increased by another 50 watts in the settings. The converter from the previous video has a rated output of only 120 watts, but can be increased to 150 watts in the settings. The left converter can output 65 volts or 9 amps, while the right one only outputs 36 volts and 6 amps. Finally, the most important difference between these converters is their circuit type. The XY6509 is a step-down converter, meaning its output cannot exceed the input voltage. The converter can operate at voltages from 12 to 72 volts, but its output voltage will naturally always be slightly lower. The XY6509 converter, however, is a completely different matter. It operates at voltages from 6 to 36 volts. It can both step up and step down the input voltage. For example, you can apply 12 volts to its input and output 36 volts. Or, conversely, apply 36 volts to the input and output 24 volts. So I hope everyone now understands that this converter is very different from the previous one, which is why I've created a separate review for it. The software in both devices is absolutely identical. All the same protections are present, and the pages scroll in the same order. The only difference is the level of the set parameters. The first one has higher ones, while the second one has lower ones. And the main character has a newer firmware version. The converter has a lot of settings, but if I were to cover them all, the video would be very long and similar to the previous one, where I talked about the SK120. Therefore, to familiarize yourself with all the features, I recommend you watch the review of the previous device. I'll leave a link to it in the description. I'd also like to add that there are currently two types of these step-down converters. The first is a powerful one, like mine, the XY6509, and the second is a slightly weaker one, the XY6506. The second has almost the same characteristics, but at 65 volts, it can only reach a maximum current of 6 amps. The resulting maximum power is approximately 390 watts. The price difference is negligible, so I recommend buying the more powerful one. Now let's take a closer look at the converter. This is what it looks like without the case. All the components are located on two boards, which are connected to each other by pin connectors. One board contains the display and digital electronics, while the other contains the powerful power components of the DC-DC converter. The display side of the board is very simple. It has a liquid crystal display, and a light diffuser fits underneath it. 3 LEDs are located on the board for backlighting. The display and diffuser are pressed against the board by a plastic frame, which is then secured to the board with 4 screws. On the reverse side are 2 microchips, a large display controller, and a small one that controls the operation of the entire module. Here is a 64 MHz processor and 64 kilobytes of flash memory, which contains the operating system, so to speak. At the bottom is a sound emitter. When buttons are pressed or any other malfunction occurs, it emits primitive sounds. By the way, there's one large XY6509 mark on the display board. This is the marking for the step-up and step-down DC-DC converter I mentioned earlier. If you compare the photos of both converters, it turns out that their boards are indeed identical. The reverse side is exactly the same. The second board doesn't have as many components, but they are all quite large and powerful. In the middle is a connector, where the terminal block is inserted. On the right is the power input, positive and negative, and on the left is the output, also positive and negative. On the left, on the output line, are two 80-volt, 220 microfarad electrolytic capacitors. Parallel to them on the reverse side of the board is another ceramic capacitor, but it's not marked. On the right, on the input line, are also two electrolytic capacitors. The first is 220 microfarads, and the second is 150. Both are 80 volts. There are two chokes wound with thick wire on the output line. The smaller one was originally wrapped in heat shrink tubing, but I removed it to see what was going on inside. Most of the space on the board is taken up by a heat sink with a fan, which holds two transistors. You can see their markings on your screens. These are N-channel transistors rated for 100 volts and 120 amps. The transistors are pressed to the heatsink via thermally conductive pads and dielectric washers. Fortunately, the screws are easily accessible. They can be tightened or loosened if necessary. The fan is connected to the board via a connector and operates on 5 volts. The fan doesn't run continuously, but only turns on when the wind turbine reaches a certain temperature or output current. Between the transistors is a powerful 5 milliohm resistor, and next to it is a temperature sensor. It measures the temperature of the DC-DC converter. You could call it a built-in temperature sensor, but the converter also has a connector for an external temperature sensor. A 10 kilo ohm NTC thermistor is inserted here. 3950B is its marking. There's another connector next to it. This is the serial communication interface. This module can be controlled from a computer using this connector. You can insert either a Wi-Fi module or a special adapter that connects to the computer via a cable here. Also nearby is a 22 microfarad, 100 volt capacitor, a choke, and two diodes. On the back of the board is a step-down DC-DC converter that reduces the input voltage to 5 volts. A rectifier diode and choke are part of its circuitry. This is a TVS diode. It is located parallel to the output of this converter. The diode is marked with two letters K. Its surge voltage is 6.3 volts. It protects devices connected to the serial port. The back of the board contains a large number of microcircuits and various electronic components. The heart of the synchronous step-down converter is this large microcircuit, marked XY6509 Here's a schematic of its wiring, taken from the datasheet. The microcircuit is supplied with a voltage of 9 to 20 volts and controls two high-power N-channel field effect transistors. An LM358 op-amp is used to measure current, and a shunt serves as a current sensor. The next microcircuit is another switching step-down converter marked EG1198. A 72-volt supply voltage is applied to its input, and a stabilized 5-volt output is obtained. 72 volts is not the limit for the microcircuit. The datasheet states that 120 volts can be applied to its input. The 5-volt output voltage powers the fan and this microcircuit. This is another switching DC-DC converter, this time a step-up one. The marking is SB6284L. The microcircuit can operate from 2 volts and boost its output voltage to 28. But here, on a working device, I couldn't get a multimeter close to this microcircuit and measure the voltage at its output. But I think it's no more than 20 volts, since this small converter is only needed to power the XY6509. After all, as I said earlier, its supply voltage shouldn't exceed 20 volts. This results in a cascade of step-up and step-down converters. The next microcircuit is an 8-pin NKS1004A. I couldn't find any information about it online. If anyone knows what this is, please let me know in the comments. Next to it is an LM321 operational amplifier. On the right side of the board are 2 more GS358 operational amplifier. These are analogs of the LM358. In the middle of the board is a high-power field effect transistor marked 100N10FG. Its full markings look like this. The transistor can withstand 100 volts and a peak current of 90 amps. In the diagram, the transistor is located at the module input on the negative line. It is controlled by a common controller. And by controlling it, you can turn on or off the current supply to the XY6509 synchronous step-down rectifier. Lower on the board at the module output is a high-power SS510 Schottky diode, rated at 5 amps and 100 volts. It is soldered parallel to the output. The cathode is to the positive and the anode is to the negative. This is a small protection measure for those occasions when a battery is connected to the converter output with the wrong polarity. If the battery has a BMS or a fuse, the diode will cause a short circuit at the output of that battery, causing the BMS to shut down and the fuse to burn out. But the module will remain intact, and the capacitors at its output won't explode due to incorrect polarity. The module's input also has a high-power diode, but this time of a different type. It's marked NR. This is a 75-volt TVS diode that protects the device from high input voltage. If the input voltage is low, this diode won't interfere with operation. But if the voltage reaches 75 volts, the diode will open and create a short circuit at the output of the power source powering the device. As a result, if the power source has a fuse, it will burn out, or simply switch to short circuit protection. As I mentioned earlier, the converter has a built-in temperature sensor and a connector for a remote temperature sensor. The remote sensor isn't included with the converter, but you can buy one separately somewhere. I have just such a one, and it looks like this. In the converter settings, you can configure the protection trip temperature for each temperature sensor. This turns off the converter output and stops current flowing to the load. The built-in temperature sensor will naturally monitor the converter's temperature, while the remote temperature sensor can be connected to another device. But the problem is that the converter's display only shows the temperature of one temperature sensor. Look, the display currently shows the converter's temperature at 38 degrees Celsius. I take the remote temperature sensor and plug it into the connector. And then the temperature reading immediately changes. Now it displays the room temperature. This can be easily verified by grasping the temperature sensor with your fingers. If I want to know the converter's temperature, how much it has heated up under load, I'll have to disconnect the remote temperature sensor. This results in an inconvenient system. Therefore, if you want to use two temperature sensors simultaneously, you'll need to build a circuit using a relay. When the relay contacts are open, the built-in temperature sensor will operate. And when the relay closes, the external temperature sensor will be connected. Now let's check how accurate the converter's output voltage is. No load is connected right now, and I'll compare it with this multimeter. The converter's output is currently off at 0 volts. I press the button, and the converter starts outputting current. The output is now 1 volt. The difference is approximately 0.06 volts. Now 5 volts. 10 volts. 15. 19. And 20. The multimeter shows 0.15 volts less. Now I need to switch the multimeter to a higher measurement range, from 20 volts to 200 volts, and continue increasing the voltage on the converter. 30 volts, a difference of 0.2 volts. 40 volts, a difference of about the same. 50. 60 volts, a difference of about 0.3 volts. And the maximum voltage of the converter is 65 volts. I forgot to mention at the very beginning that I'm currently supplying 73.2 volts to the converter input, even though the maximum input voltage is stated to be 72 volts. Now let's see how accurately the converter shows the output current. A 5-volt current is currently being applied to the load. But I won't connect any load. I'll short-circuit it using this multimeter. Its switch is set to measure 10 amps. I short-circuit it. The voltage drops. My converter stabilization current is set to 100 milliamps. The multimeter shows approximately 90 milliamps. Now it's 500 milliamps, and here it's 480 to 490. Now it's 1 amp. 2. 3. 4. 5. 6. 7. 8. 9. And the maximum current is 9.1 amperes. Now let's move on to the actual testing of the device. We'll connect a load to it. We won't be looking at low voltages. I'll set the output to 60 volts straight away, since it's clear that if the device can handle a high voltage load, then it's fine at low voltage. I don't think there's anything to look at there. This multimeter is connected to the converter output and will duplicate the output voltage. The readings on it and the converter can be compared. Sometimes it happens that a converter displays one voltage on its display, but its output shows a completely different voltage. This multimeter is also connected to the converter, but will display the load current. Behind the scenes, I'm connecting a nichrome coil. Current 2.9 amps, load 175 watts. The voltage doesn't drop. I increase the load further. 380 watts, current 6.3 amps. I increase the load even further. 537 watts. The current is almost maximum, 8.9 amps. As you can see, even under such a colossal load of half a kilowatt, the voltage at the converter's output doesn't drop. This is a very good result for such a small thing. Now let's look at the same thing, but the output voltage is now 62 volts. The multimeter that was displaying the current had to be removed from the circuit because the wires started melting due to the high current. I connect the load. Current 8.9 amps, load 550 watts. Now I'll increase the voltage to 63 volts. The current has become 9 amps, load 566 watts. The input voltage has dropped. It's currently at 68 volts. The difference between input and output is 4.5 volts. Now I'll leave the converter under this load for a few minutes and then see how hot it gets. And here I'll speed up the video. 5 minutes have passed. The output capacitors are slightly warm but not hot. But the small inductor is very hot, it burns my finger. The input capacitors are also slightly warm. The large inductor is hot, but it doesn't burn my fingers. The heatsink with the transistors is also, surprisingly, barely warm. The temperature sensor, located on the board near the transistors, shows a temperature of 49 degrees Celsius. I increase the voltage to 64 volts. I connect the load. The current is 6.5 amps. 7.3 amps. 8 amps. But at 8.6 amps, the voltage dropped from 64 to 63.5. The input voltage dropped to 68. The difference between the input and output is 4.5 volts. If I reduce the load and increase the current to 7.8 amps, the voltage recovers. I'll increase the output voltage to its maximum of 65 volts. The current is 6.8 amps. The load is 443 watts. The output voltage has dropped by half a volt. I'll try reducing the load. I'll increase the current to 5 amps. The load is 325 watts, but the voltage doesn't drop. I'll increase the load slightly. The current is 5.8 amps. The voltage remains stable. But if I increase the load slightly, the voltage drops at 6 amps. I'll reduce the load slightly. The current is 5.9 amps, but the voltage remains stable. The input is now 69 volts. The difference between the input and output is 4 volts. I recorded all the data from my tests in this table. At 62 and 63 volts, I managed to get almost the maximum current of 9 amps. The load was 553 and 570 watts. At 64 volts, I got 8 amps and 507 watts. At 65 volts, only 6 amps and a load of 383 watts. At these two voltages, the current can be higher, but the voltage begins to sag under load. But it's too early to say the converter is bad and doesn't deliver its stated performance. Most likely, the reason for these poor results is the switching power supply I used to power this step-down converter. At idle, without a load, it produces 73 volts. But under load, the voltage begins to sag. It drops below 68 volts. Perhaps if I had a good power supply that would produce a stabilized 72 volts, even under heavy load, then this step-down converter could perform at its full capacity. I could get 65 volts and 9 amps, a total of 585 watts. We can't get more than that. Even though we set the converter's power protection to 600 or even 650 watts. I have already shown how accurately the converter stabilizes the output current. But how quickly this happens is another question. I think many people know that if a power supply or converter has very large smoothing capacitors at the output, the short circuit current will be enormous, much greater than the power supply itself can handle. And until the output capacitor discharges, the current will exceed the set value. Something similar is happening here, only the problem is a little more complex. Current regulation is triggered according to your setting, but it doesn't happen immediately. Let's take a look at this. The voltage at the converter output is currently 5 volts. A multimeter set to 10 amps is connected to the converter output. I'll use it to short-circuit the converter wires. This will result in the short-circuit current being displayed on both the converter and multimeter. When I short-circuit the wires, you'll need to compare the readings on both devices. The current is now limited to 100 milliamps. I short-circuit the wires and see what happens. For the first few seconds, the multimeter shows a lower current, not 100 milliamps, but about 60, but then it recovers to the set value. I disconnect the wires, wait a couple of seconds, and short-circuit them again. Now the current is 130 milliamps. The current has dropped again and seems even lower than last time. I short-circuit the wires again, and the current is immediately correct. Now let's see what happens if I leave the wires short-circuited and open and close the converter output. In this case, the output capacitors should be constantly discharged. I open the output. The current is 100 milliamps, as expected. Now the same thing, but with a current of 1 ampere. I short-circuit the wires and observe. For the first fraction of a second, the current is 2 amperes, then drops to 270 milliamps, and then settles as expected. I open the wires and try again. This time, the current is 1/4 higher, but then immediately recovers. I try again. The current is initially less than 1 amp, but then recovers. Next try, and here the current is almost twice as high. But then it also drops. Now I try the same thing, but with the wires shorted, and open the converter output. The current holds 1 amp correctly. I close the output. I open it again. Everything is fine. Now it's the same as before, but with a current of 5 amps. I short the wires, and for the first couple of seconds, the current is twice the set value. Then it drops. I short the wires again, and the current is immediately normal. I short them again, the current is 5 amps. Now I immediately short the wires and open the output. The current is 5 amps. I close the output again and open it again. And everything is fine too. Now the same thing, but with the current set to 9 amps. I short circuit the wires, and for the first couple of seconds the current is only 3 amps. But then it rises to the expected 9 amps. I short circuit the wires again. And here, at first the current is only 800 milliamps, but then it rises to the expected 9 amps. I open the wires and short circuit them again. Here, in the first fraction of a second, the current doubled. Then the current dropped to 7 amps and reached the required 9 amps. I short-circuited the wires again. Again, the current doubled, and this time it lasted longer. Then the current dropped to 9.3 amps, and smoke began to come out of the multimeter leads. Now I'll try it with the wires shorted. I open the output, and the current is slightly higher than set, almost 9.4 amps, but then it drops to 9.1 amps. I close and open the output again. The current immediately returned to 9.1 amps as set. And here's another example. Here I short-circuited the wires and set the current to 30 milliamps. As you can see, the current is constantly fluctuating for some reason. Sometimes it rises to 30 milliamps, sometimes it drops to 7. This is also very strange behavior. Personally, I don't use such low currents, but it will probably be very important to someone. Now let's draw a conclusion based on what we've seen. The converter's current regulation works, but not as well as we'd like. The current does not exceed the set values if the load is first connected to the converter output and then power is applied to it. In this case, everything will be fine. However, if you connect the load to an open output, the current surge can be very strong, although this does not always happen. In this case, the device may blatantly lie to you and show on the display that everything is normal. That's all for today. Like and subscribe to the channel if anyone hasn't already. Ask questions in the comments if anything is unclear. In the description, I left a link to AliExpress, the store where you can buy the XY6509, and also a link to a video review of the XY6509 converter. If anyone hasn't watched it yet, they can watch it.